What if I told you that SpaceX's newest Starship just delivered its most impressive performance yet, and one of its biggest failures at the exact same time? After 7 months of waiting, a brand new Starship finally roared off the launch pad with more power than ever before. The launch looked nearly perfect. The engines ignited, the rocket accelerated faster than any previous Starship, and SpaceX appeared closer than ever to making its Mars dream a reality. But then something unexpected happened. The booster began losing engines. Systems started failing. And within minutes, one of the most advanced rockets ever built was fighting for survival. So was this launch a giant leap toward Mars, or a warning that SpaceX still has major problems to solve? Today, we're breaking down every major moment of Starship's latest flight, from the incredible liftoff and dramatic booster failure to the stunning achievements in space that could change the future of human exploration forever. Because what happened on this mission wasn't just another rocket test, it was a glimpse into the future of spaceflight. For more than 7 months, SpaceX's Starship program remained silent. After the previous flight in October 2025, no massive rocket launches shook the skies above Starbase, Texas, and no new test missions captured the attention of space enthusiasts around the world. To many people, it seemed like progress had slowed down, but behind the scenes the opposite was happening. Engineers, technicians, and designers were working relentlessly on what would become the biggest upgrade in Starship's history. SpaceX wasn't simply preparing another test flight, it was rebuilding key parts of the entire system. The company introduced a redesigned Starship upper stage, an upgraded Super Heavy booster, a new generation of Raptor engines, and a completely revamped launch infrastructure. Every major component of the vehicle had been improved with one goal in mind: bringing Starship closer to becoming a fully reusable spacecraft capable of carrying humans to the Moon, Mars, and beyond. The anticipation surrounding this launch was enormous because it represented far more than a routine test. This was the first opportunity to see whether months of engineering work would translate into real-world performance. Expectations were high, but the mission encountered trouble before it could even leave the ground. During the first launch attempt, the countdown proceeded normally as propellant flowed into the rocket and all systems appeared ready for liftoff. Then, unexpectedly, the launch was halted. A problem developed with the quick disconnect arm, the structure attached to the launch tower that supplies fuel and other connections to the upper stage. Just before launch, the arm is supposed to retract safely away from the vehicle, but a stuck pin prevented it from moving. Without the arm retracting properly, launch was impossible, forcing SpaceX to abort the attempt and stand down. Although the scrub was disappointing for millions of viewers watching around the world, it also demonstrated one of SpaceX's greatest strengths: speed. Rather than delaying for days or weeks, teams immediately began working to solve the problem. Engineers inspected the mechanism, identified the issue, and spent the night making repairs. Within a remarkably short period of time, the launch system was reset and prepared for another attempt. The quick turnaround highlighted the company's philosophy of rapid testing and rapid improvement. Every delay, every malfunction, and every unexpected issue is treated as a learning opportunity rather than a major setback. The brief delay also provided an interesting look at one of Starship's most impressive upgrades: its fueling system. During preparations for launch, SpaceX demonstrated the ability to fully fuel the largest rocket ever built in approximately 30 minutes. That achievement is significant because Starship uses super-cold cryogenic propellants that naturally warm up and evaporate over time. The faster a rocket can be loaded with fuel, the less propellant is lost and the more efficient the launch operation becomes. This capability is especially important for SpaceX's long-term vision, which involves launching Starships frequently, potentially multiple times per day. Such a launch rate would be essential for supporting large satellite deployments, orbital refueling operations, lunar missions, and eventually human expeditions to Mars. When launch day finally arrived again, there was a sense that something historic was about to happen. Months of preparation had led to this moment. A new rocket, a new booster, new engines, and a new launch pad were all about to face their first real test under flight conditions. The countdown resumed, the fueling process proceeded flawlessly, and this time there were no last-minute issues. As the clock moved closer to zero, anticipation continued to build. SpaceX had spent 7 months preparing for this flight, and now the world was finally about to discover whether those months of work had brought Starship one step closer to transforming the future of space exploration. As the countdown continued toward liftoff, one of the most important upgrades of the entire Starship program was sitting directly beneath the rocket. While most people were focused on the massive vehicle towering above the launch site, SpaceX engineers understood that the launch pad itself represented a major step forward. Previous Starship launches had revealed just how difficult it is to operate the most powerful rocket ever built. The immense force generated by dozens of Raptor engines created extreme heat, pressure, and acoustic energy capable of damaging the infrastructure below. Early test flights produced dramatic scenes of debris, dust, and concrete being blasted away from the launch area. Although those launches were successful in gathering valuable data, they also showed that SpaceX needed a more durable solution if Starship was ever going to support frequent operations. The new launch pad was designed specifically to solve those challenges. Instead of relying on earlier experimental systems, SpaceX constructed a far more advanced foundation capable of handling the tremendous power of the Super Heavy booster. Reinforced concrete and steel structures were integrated into the pad, creating a stronger platform that could survive repeated launches with minimal maintenance. Most importantly, the company introduced a significantly upgraded water deluge system. During liftoff, enormous amounts of water are pumped beneath the rocket to absorb heat, reduce acoustic shockwaves, and protect critical infrastructure from damage. Combined with specially designed flame trenches that direct exhaust away from the launch mount, the system helps manage the incredible energy released during ignition. These improvements are about much more than simply protecting the launch site. They are a key part of SpaceX's long-term strategy for rapid reusability. Traditional rockets may launch only a handful of times each year, giving operators plenty of time to inspect and repair facilities between missions. Starship is intended to operate at a completely different scale. Elon Musk has repeatedly stated that future Mars missions will require thousands of launches, meaning SpaceX must eventually achieve an airline-like model of operations where rockets can launch, return, and launch again with minimal downtime. A launch pad that requires extensive repairs after every flight would make that vision impossible. The upgraded infrastructure is therefore an essential piece of the larger plan to make space travel routine and affordable. Another impressive demonstration of progress came during fueling operations. Despite being the largest rocket ever constructed, Starship was fully loaded with cryogenic methane and liquid oxygen in roughly 30 minutes. This rapid fueling capability represents a significant engineering achievement. Cryogenic propellants must be kept at extremely low temperatures, and any delay increases the amount of fuel lost through evaporation. By dramatically reducing fueling time, SpaceX improves efficiency while also moving closer to the fast turnaround times required for future high-frequency launch schedules. Compared to many traditional launch systems that require several hours to complete fueling, Starship's speed highlights how different SpaceX's operational approach has become. As the final minutes of the countdown approached, excitement continued to build. Everything appeared to be functioning exactly as planned. The launch pad systems were performing flawlessly, the fueling process had been completed successfully, and the upgraded vehicle stood ready for its first true test. After months of development and a delayed first attempt, the stage was finally set. In just a few moments, the world would witness whether SpaceX's new infrastructure, new engines, and new rocket design could deliver on the promise of pushing humanity one step closer to becoming a spacefaring civilization. The countdown reached its final seconds, and the most powerful launch system ever created prepared to come alive. As the countdown reached zero, the moment everyone had been waiting for finally arrived. Beneath the Super Heavy booster, all 33 Raptor version 3 engines roared to life in a spectacular display of power. Unlike previous Starship flights, where engine ignition occurred in stages, this upgraded booster ignited all of its engines almost simultaneously. The result was breathtaking. Within an instant, the launch pad disappeared beneath a massive cloud of steam and exhaust as the most powerful rocket ever built began its journey toward space. The ground shook, the tower trembled, and Starship lifted off with a level of acceleration that immediately set it apart from earlier flights. The difference was obvious from the very beginning. Thanks to the upgraded Raptor V3 engines and improvements throughout the booster, Starship climbed faster and more aggressively than any version before it. In less than a minute, the vehicle had already reached extraordinary speeds while rapidly gaining altitude. Engineers had hoped the new engines would provide more thrust, greater efficiency, and improved reliability, and during the opening moments of flight they appeared to be delivering exactly that. Everything looked smooth, stable, and under control. For spectators watching around the world, it seemed as though SpaceX's months of development work were paying off perfectly. As Starship continued its ascent, attention shifted toward one of the most critical events of the mission: hot stage separation. This maneuver is one of the most unique aspects of the Starship system. Unlike traditional rockets that separate stages after shutting down their engines, Starship ignites the engines of the upper stage while it is still attached to the booster. This allows the rocket to maintain continuous acceleration and maximize performance. It is an incredibly complex procedure that requires precise timing and engineering. Any mistake could jeopardize the mission, making it one of the most anticipated. When the time came, the upper stage engines ignited successfully. Brilliant plumes of exhaust burst from the ship as it pushed away from the booster, and the separation occurred exactly as planned. It was another major milestone achieved. The upper stage continued accelerating toward its target trajectory while the Super Heavy booster began preparing for its return sequence. At this point, the mission appeared to be progressing almost flawlessly. However, only seconds later, the situation changed dramatically. The booster initiated its boost-back burn, a maneuver designed to slow the vehicle and guide it toward its planned landing area. To perform this burn, multiple Raptor engines needed to restart after separation. At first, the ignition sequence appeared normal, but almost immediately problems began to emerge. Several engines failed shortly after reigniting. Then more engines shut down unexpectedly. What should have been a powerful and controlled burn quickly turned into a growing technical problem. Instead of producing the thrust required to slow the booster, engine failures began reducing its ability to control its descent. Within moments, it became clear that something was seriously wrong. The number of operational engines continued to decrease, and the booster was no longer performing the maneuver as intended. Camera views showed unusual flashes and signs of instability near the engine section. The vehicle, which had looked so powerful and capable only minutes earlier, was now fighting to maintain control. Engineers and viewers alike knew that without a successful boost-back burn, the booster would be unable to follow its planned trajectory. As the booster fell back toward Earth, onboard cameras captured increasingly dramatic scenes. The vehicle began experiencing intense aerodynamic forces as it descended through the atmosphere. Heat built up around the structure, vibrations increased, and the rocket appeared to be struggling against conditions it was no longer fully prepared to handle. Then came the final indication that the situation had reached a critical point. A bright flash appeared near the base of the booster, followed by the sudden loss of camera feeds. The signal disappeared, strongly suggesting that the vehicle had broken apart or exploded during its descent. For SpaceX, this was a disappointing outcome. One of the primary goals of the upgraded booster design was to improve reliability and eliminate many of the engine-related issues seen on previous flights. Yet despite an outstanding launch and successful stage separation, the booster had suffered a major failure during one of the most important phases of the mission. However, while the loss of the booster was a setback, the story of this flight was far from over. High above Earth, the Starship upper stage was still flying, and it was about to demonstrate some of the most important improvements SpaceX had ever made to the spacecraft. While the dramatic booster failure was capturing attention on the ground, the Starship upper stage was continuing its journey high above Earth. In many ways, this was where the most important part of the mission truly began. The booster's job was to provide the initial push off the launch pad, but the upper stage is the vehicle that will eventually carry satellites, cargo, astronauts, and perhaps one day entire crews traveling to the Moon and Mars. As a result, all eyes now turn towards Starship itself to see whether it could deliver on the promise of its newest upgrades. At first, everything appeared to be going according to plan. The ship maintained a stable trajectory and continued accelerating toward its target velocity. The new Raptor V3 engines were performing well, and the vehicle seemed healthy. However, only a short time after stage separation, another challenge emerged. One of Starship's 6 engines unexpectedly shut down. For many viewers, this immediately raised concerns because previous Starship failures had often started exactly the same way. A single engine problem would trigger a chain reaction, leading to additional failures, loss of control, and eventually the destruction of the spacecraft. Given that history, seeing an engine go offline was an alarming moment. But this time, something was different. Instead of spiraling into a larger crisis, the vehicle remained stable. The remaining engines continued operating normally, and Starship kept accelerating. The failure was successfully isolated, preventing it from affecting the rest of the propulsion system. This may not have looked dramatic from the outside, but from an engineering perspective it was one of the most significant achievements of the entire mission. It suggested that the upgrades SpaceX had made over the previous months were working as intended. Rather than allowing one problem to cascade into a complete vehicle loss, the spacecraft was able to absorb the failure and continue flying. As the ship climbed higher and higher, confidence began to grow. The vehicle successfully approached its planned velocity, demonstrating that even with one engine unavailable, it still had enough performance to achieve its mission objectives. Eventually, the remaining engines completed their burn and shut down normally. There were no explosions, no uncontrolled spinning, and no signs of a major malfunction. Compared to previous flights that had ended prematurely, this represented a major step forward in Starship's development. With the ascent phase complete, the mission moved on to another critical objective, payload deployment. Inside the spacecraft were 20 Starlink simulator satellites designed to mimic the size and weight of future Starlink version 3 satellites. These test payloads were not intended to provide communication services. Instead, they existed to verify that Starship's new deployment system could successfully release cargo in space. One by one, the simulators were deployed from the payload bay, demonstrating a capability that will eventually become essential for Starship's commercial operations. Successfully launching large numbers of satellites is one of the primary reasons SpaceX is developing the vehicle, making this demonstration an important milestone. The mission then delivered one of its most memorable moments. Alongside the satellite simulators were 2 special payloads equipped with cameras. After deployment, these cameras captured a view that had never been seen before, a satellite looking back at Starship itself while both were in space. The footage provided a stunning perspective of the spacecraft against the backdrop of Earth, offering viewers a glimpse of what future orbital operations could look like. The images were not only visually spectacular but also symbolic of how far the Starship program has progressed. What once existed only as concept art and ambitious promises was now operating in the environment of space. By this point, the mission had already achieved several important objectives despite the loss of the booster. The upper stage had survived an engine failure, reached its target conditions, deployed payload successfully, and demonstrated new operational capabilities. These accomplishments showed that while significant challenges remained, Starship was steadily becoming a more capable and resilient spacecraft. The final test, however, was still ahead. To truly prove its progress, the vehicle would need to survive the intense heat and pressure of atmospheric re-entry and attempt another controlled landing in the waters of the Indian Ocean. That challenge would determine whether this flight ended as a partial success, or as one of the most encouraging Starship missions to date. With its payload deployment objectives completed and several major milestones already achieved, Starship entered the final phase of the mission. This stage would test one of the most important capabilities needed for the future of the program: the ability to survive re-entry through Earth's atmosphere. While reaching space is an impressive achievement, the true promise of Starship lies in reusability. SpaceX's long-term vision depends on a spacecraft that can launch, complete its mission, return safely, and fly again with minimal refurbishment. Every successful re-entry brings that vision one step closer to reality. As Starship approached the upper layers of Earth's atmosphere, it began one of the most visually spectacular maneuvers in modern spaceflight. Traveling at thousands of kilometers per hour, the spacecraft encountered increasingly dense air, creating extreme friction and temperatures around its surface. Plasma formed around the vehicle as the atmosphere compressed and heated during descent. Thanks to Starlink connectivity, viewers around the world were able to watch this process unfold in real time, something that was impossible during the era of the Space Shuttle. The glowing vehicle streaking through the atmosphere has become one of the defining images of the Starship program, showcasing both the beauty and difficulty of returning from space. The spacecraft endured the intense heating phase remarkably well. Throughout previous test flights, the heat shield had often been a source of concern, with tiles becoming damaged, falling off, or showing signs of severe wear after re-entry. This time, however, the situation appeared much improved. As Starship emerged from the hottest portion of its descent, onboard cameras revealed a vehicle that remained largely intact and under control. The heat shield showed significantly fewer signs of damage than seen on earlier flights, suggesting that SpaceX's continuous refinements were producing real results. For engineers focused on building a fully reusable spacecraft, this was encouraging news. As the vehicle descended further, it transitioned into its unique atmospheric flight profile. Using its large flaps, Starship maneuvered through the atmosphere while maintaining control of its direction and speed. This phase is critical because future operational missions will require the spacecraft to precisely guide itself back to the launch site for recovery. The flight path resembles a controlled skydiving maneuver, allowing the vehicle to slow down efficiently before preparing for landing. Every successful test of these aerodynamic systems provides valuable data that will eventually support catch attempts using the giant mechanical arms of the launch tower. The final challenge came as Starship prepared for landing. To complete the maneuver, the spacecraft needed to relight its engines, rotate into a vertical position, and slow itself enough for a controlled splashdown in the Indian Ocean. This transition is one of the most technically demanding moments of the entire flight. As the vehicle approached the water, engine ignition commands were sent. 2 of the 3 center Raptor engines successfully restarted, providing enough thrust to control the descent. The maneuver was not perfect, but it was effective. Starship slowed dramatically and touched down in the ocean largely intact. Moments later, as expected during these test missions, the spacecraft tipped over after splashdown and was eventually destroyed. However, by that point, the mission had already delivered most of the data SpaceX needed. More importantly, it had demonstrated meaningful progress in several critical areas. The ship survived ascent despite losing an engine. It completed payload deployment objectives. It endured atmospheric re-entry. It performed a controlled landing sequence. And it returned with one of the healthiest-looking heat shields ever seen on a Starship vehicle. So what does all of this mean for the future? The answer is both encouraging and challenging. On one hand, the mission highlighted major improvements across the Starship system and showed clear progress toward full reusability. On the other hand, the booster's engine failures revealed that significant work remains before SpaceX can achieve its most ambitious goals. Planned milestones such as catching the booster with the launch tower, conducting orbital refueling demonstrations, deploying operational satellites, and eventually sending crews beyond Earth orbit all depend on solving these reliability issues. Yet this flight also demonstrated something that has defined SpaceX throughout its history: progress through testing. Every launch provides new information, every failure reveals weaknesses, and every success pushes the technology forward. While the booster's loss was disappointing, the overall mission showed that Starship continues moving closer to becoming the revolutionary spacecraft it was designed to be. The road to the Moon, Mars, and beyond has never been easy, but with each test flight, SpaceX gains the experience needed to make that future possible. The next Starship launch will carry even greater expectations. Engineers will analyze every second of data from this mission, identify the causes of the engine failures, and implement new improvements. When the next vehicle rolls out to the launch pad, it will represent another step in the ongoing journey to build a spacecraft capable of changing humanity's future in space. And once again, the world will be watching.